a little bit of a look now at 11 from this one here. How can you find the uncertainty for something like a stopwatch? So for a stopwatch, you can only estimate it. Yeah, we say estimate, but let's guess it. So I don't know. We think that when you press start, and then you have the time running, and then you press end, there's a little bit of a delay at the two ends. Start, stop. So I think 0.25 seconds is a reasonable number. But don't forget, in the pendulum experiment, you did it for 10 oscillations. So the good news is, this is for 10, so actually just for one of them, it will be 0.025 seconds, which isn't actually that bad.
Oh, for one.
For one cycle, yeah, so that's actually alright. Okay. 12. Now, for something like a meter stick, the uncertainty for an instrument like a meter stick, the uncertainty is half the smallest value you feel you can accurately read on a meter stick. You could probably read half a centimeter with not much difficulty on a meter stick, maybe even more, or maybe even smaller. So for me, I'd say it's about half of 0.005. So 0.0025 meters is what I'd say it will be for a meter stick. Okay. Now for a voltmeter, the thing with the voltmeter is the voltage is moving between two numbers. So for a voltmeter, we'll say the uncertainty is going to be the max value minus the min value over 2. Yeah. No, actually, average would be plus. Yeah, so that's 11, 12, 13. And just to recap, 14, the relative uncertainty is just the uncertainty divided by the value, the average. That's the relative one. Okay. This has no units. That's one of its advantages. So you can actually give it as a percentage. And then relative error, that's the true value minus the estimated value from your experiment, divided by true value, multiply 100%. Something that you need for experiment 2, because that's where you're calculating G. So you should report this in your results at the end, because you know what G should be. Yeah. And also, yes, also you could do it for experiment 4, because you know what the mass should be, which you're predicting from the data. But you can't really do it for experiment number 3, Ohm's law, because I don't tell you what the resistor value is, the resistance is. So you have no way of knowing the true value. Now I told you that I believe it to be roughly 1 ohm, because that's how much the person on eBay said it is when I bought it from them. But I don't know if it's exactly 1 ohm. Okay? Right, now, will we do 15 with the calculations? Yeah? Or 16, I mean. Yeah. So 16, for the pendulum, the uncertainty in its length is 0.005. The average length is 0.55. The uncertainty in the time is 0.01 second. I think this is a little too big, because what did we have a moment ago? It should only be, oh no, okay, I guess it's not. And then the average time is 1.419 seconds, and then from your experiment you estimate G to be 9.8. This is the estimate. Okay, so part A is what is the relative uncertainty of L. So that is delta L over L. Can you tell me this number, please? What do we have?
9 times 10 to minus 3.
9 times 10 to the minus 3?
9.09 times 10 to minus 3.
Yeah. So if I divide that by, wait, hang on. What's that the decimal size? 0.00909, yes? So that's not even 1%, you know, that's approximately 1%. So that's, you know, that's okay. It's not bad, 1%. Relative uncertainty. B, for T, what did I say it is? 0.01 over 1.419. What's this number? I think this would be much smaller, is it?
7.05 times 10 to minus 3.
Ah, so again, this isn't even 1%. This is more like 0.75%. It's quite small again. So we'll just say less than 1%, less than 1%. Okay. C, for G, oh sorry, I'm asking for the
relative uncertainty of activity.
did I mean to say relative error? Sorry, yes, delta G over G. So what do we know? Oh, we don't. This is where we have to use our formula, sorry. Yeah, so now we have this formula. G, I gave it, well, I'll have to rewrite it. We have T equals 2 pi root L over G. So that means T squared equals 4 pi squared L over G. So that means G equals 4 pi squared L T minus 2. If I rearrange it. Yeah? Yes? Okay? Yeah. So then we have this formula. Delta G over average G, that is square root. Now, this here, there's no uncertainty because it's a constant, so we don't consider it. The L, it is power, let me write it in 1. So if we want, it is 1L, sorry, delta L over L squared plus minus 2 delta T over T squared. Now, that's nice because we have this and this already. And we have delta G over G equals square root. So what was my first? It's my first answer. The answer from A squared plus 4 times the answer for B squared. And then we can multiply this answer by the G there. So delta G is 9.8 square root the answer from A squared plus 4 times the answer from B squared. Can you tell me what that number is, please? 0.164. Yeah? Okay? Good. So that's not so bad. We can say G is 9.8 plus or minus this number, 0.164. Okay. Oh yeah, which is actually the next part. We think that the true value for G will be somewhere between 9. Sorry, this is E. Oh, with bounds. Yeah, that's what I'm doing here. It's 9.8 plus 0.164 or 9.8 minus 0.164. No, this is C. Hang on. Oh, sorry. Yeah. I did kind of. So this is actually the answer for D, and the answer for C is the relative one, which is, in other words, sorry Tal, the answer for C is just this piece here. It was this here. So I don't know what that is. What is it? What was just the square root piece before the 9.8? Well, if you do this number divided by 9.8, what do you get? 0.0168. That's this piece here.
What you gave us relative uncertainty uncertainty.
Yeah, uncertainty divided by the mean, and from the formula it's just that square root piece. That's the relative uncertainty here, because look, there it is there, delta G over G equals this. And then in the next part,
What the mean value of G is
9.8. It's given to us.
or you can divide it by G, the square root by G.
Here? Yeah, you're right, because relative is this over this, which is equal to this. That's our formula. Here, if I go back a step. This is the formula for relative uncertainty in G. We can bring the G up here to make it uncertainty then. That's what's happening. Sorry, I did skip that piece there. Okay, what are the two numbers here, please? 9.964, and then here 9.736. Is that right? How? What is it?
Should be 6. 6 or 3, 6.
9.736. Is that what I had? Dude, just type it on the calculator.
636.
Thank you. Yes. Okay, so we think G to be between these two numbers. Okay.
Can we just try to do this plus minus?
Yeah, that's okay. I just think it's good to see what it is. How precise do you feel this number is?
We don't know.
In your opinion.
But how do we know? We don't know the...
If the true value is 9.81, which we can look up, how precise do you think the 9.8 estimate is with these bounds? Well, remember, precise is how close we are to a value, which may or may not be true. So what do you think? Plus or minus 0.164? Well, why don't we make it a percentage? What's 0.164 divided by 9.8? What's that as a percentage of the value? I mean, I don't think it's too bad. What is it?
1.6.
So 1.6%?
Yeah. 1.7.
Okay, it's not very precise because there's more than 1% error. More than 1% is the difference, either side. So I would say it's not very precise. But, and this is the big but, it is very accurate because we got 9.8 and the true value is 9.81. So it is accurate but not so precise.
If our experiment has more than a 2% error, is that wrong?
No, it's not wrong. Like, I mean, the smallest, yeah, you just failed physics. Really, ideally you should always try to have less than 1%, okay? But sometimes it's not possible, so you might have 1 or 2%. But once you start going past 2%, it means maybe either something was calculated wrongly or maybe the equipment wasn't used as carefully as it should have been, you know. But I mean, it's not going to cost you any marks significantly. It won't even cost you any, yeah? Yes. So for F and G, it is accurate, but not very precise. Okay. And then the last one, H, is the relative error. So that's 9.81 minus 9.8 all over 9.81 times 100 over 1. What's that, please? 0.102%. Which is very good. Very, very good. A tenth of a percent. Excellent. Yeah. We happy? We happy. Okay, so we'll go on to the next lesson now. So last time we talked about density and what usually follows. So density is pressure, which some people know already. Does anyone know the definition of pressure? Anybody? Yeah. So the idea for pressure is you have an area and you have a force, and the pressure is the force per unit area, or as a formula, pressure is force divided by area. What's the unit for pressure? Yeah, the unit for pressure is newtons per meter, but we call 1 meter squared, 1 newton per meter square a Pascal, or PA for short. So for example, 12 PA, that would be 12 newtons per meter squared. You doing okay, you alright?
Yes.
You're looking sick, man. You okay? No. Alright, so we call Pascals. Now, we use Pascals, you mostly hear it when we're talking about the weather. So in fact, right now, can I scroll down? You have this? Yeah. So right now, you don't feel it, but you have all this air pushing down on you. Does anybody know roughly what the pressure?
1 times 10 power.
Yeah, it's something like 1.01 times 10 to the 5 pascals. Which, if you think about it, that is 101,000 newtons per meter squared. Now you might say, well, how come I don't feel 101,000 newtons per meter square? And the reason is because we are built like this. We are built not to notice it, because every living thing feels this pressure, and it's always been this way. So things have just adapted not to notice it. Okay? But if we imagine some kind of alien from a different planet coming here, they possibly could feel this pressure a lot more than us, or less, depending. So it's difficult to imagine right now pushing down on me is 101,000 newtons per meter squared, which seems like an awful lot, doesn't it? But it really is that much. Okay, it's a really large number. And as you know, on different days, the weather causes small changes in this. So when the weather is like today, do we know if the pressure goes up or down?
No.
Yeah, pressure goes down. So a day like today, this will be smaller than this number, and on a sunny day, it will be bigger than this number.
Why?
Okay? I don't know, ask the weatherman.
So,
High pressure is good weather, sunny weather, low pressure is bad weather. Yeah, you know, just remember it this way, high is good. Interpret that as you like. Okay. So that is how I always remember it, okay? Right. Let's see, okay, so a bit more with pressure. Why is pressure important? Well, for example here, if we have 10 newtons on 1 meter, or the same 10 newtons on 1 centimeter squared, imagine this is like a person's skin, and I put 10 newtons on 1 meter on them, or I put 10 newtons on 1 centimeter squared. It's the same force, isn't it? But which do you think hurts more? The smaller one, yeah? So, you know, if I have 1 millimeter squared, I think the pressure will be so great that the skin probably will be broken. So what I would like people to do now for me is compare the 3 situations. Give me the pressure. Here's my 10 newtons, but now on 1 millimeter squared, and this is skin, and this is the force. So can you give me the pressures? Well, the first one will just be 10 pascals, but I'd like these two as well. If you can calculate this for me. Yeah, well, for centimetre it's 10 to the minus 2 all squared, so that'd be 10 to the minus 4. And then milli is 10 to the minus 3 all squared, so it's 10 to the minus 6. It's a significant difference, isn't it?
yeah. 10, 1,000, 10,000.
Huh? Yeah, well, let's calculate it now. So,
10 to 5 is the normal pressure.
yeah. Oh no, but I want for these situations here. Yeah. This is just a person pushing something on someone's skin.
Yeah.
Which one?
The centimeters one would be
Centimetre one is about, is it 10 to the 5, is it? Yeah. So let's have a look here at the second one. Pressure is force over area, which will be 10 over 10 to the minus 2, that's a centimetre squared, so that's 10 to the 5 newtons. And then the next one is pressure is force over area, which is 10 over here? Oh, yes. Yes, because this is a 10 here. Yeah. 10 to the minus 3 squared, so that's 10 to the 7 newtons. Sorry, not newtons, sorry. Pascals. Or newton per meter squared, yeah. So,
is there anything else that we can...
Could we atmosphere?
Yeah, for sure.
well, yeah, this is usually the thing, like, we don't feel the atmospheric pressure, so we just care about the extra on top of it. But you're right, if you were wanting the total pressure, you now would have to add the atmospheric pressure to it. So in this case here, it'd be 2 times 10 to the 5. In this case here, the 10 to the 5 doesn't add much to this, so it's still roughly 10 to the 7.
Which pressure do we get from the weather broadcast? In atmosphere and pascals?
Oh, it depends what country and weather station.
Here? On TV usually, what weather is?
I don't know, because I don't actually watch the weather on TV. But I think when I do check the weather online, I always set my preferences for kilopascals. So that's the one I always use. So it is kilopascals is what I see. But now some countries use atmosphere. And then there's also bars as well. Maybe.
But bars is usually for the water when you go deep.
Yeah, but I will always use pascals, and in the exam it will always be pascals, or newtons per meter squared. Okay, well, since we're talking about weather, then we'll have a look at pressure for water. Okay, I'll scroll down. Can I scroll down? Yes? Right, let's have a look at an interesting example here, and we'll do the one with the water actually. Okay, so let's imagine, just to make this easy, we have, it's maybe hard to tell, but this is a circle in the water, like a coin, and I'm decreasing it. Okay? Whoops. What's wrong? What? What's wrong?
Nothing.
No, really, what's wrong? I heard 35.
Time goes very slow.
I'm sorry about this. Okay, so we have a coin, and the coin is being dropped into the water. I want to know the pressure on the coin. Okay, so formula for pressure is force over area. If this here is or, then at least we have the area. It is pi r squared. But what's the force? Well, the force is the water above it pushing down. So if you think about it, it's actually just the weight of this water. Yeah, that's what we're going to get to. No, that's all. Hang on. One step at a time. So it's the weight of the water above the coin pushing down on it. That's the force. Okay, what's the formula for weight? It's mg. Now, we have density is mass over volume. So mass is density by volume. So this is density volume g over pi r squared. Now the volume, what shape is this? The cylinder. So this will be density pi r squared h g over pi r squared, which equals density g and h. But what is really interesting is, notice how the or has disappeared. So it doesn't matter about the value for the or, you still get the same formula here. So now what we do is we make or equal to 0. So we've changed it into this type of problem. So we have a point, and the point is at a distance, a depth of h. The pressure it feels in the water is equal to the density times gravity times h. So notice that as I increase the h, what happens to the pressure? Increases. Likewise, if I make the liquid denser, what happens to the pressure? It also increases. So for example, if here is water, and I replace the water with something more dense, yes, okay, we'll go with melted steel. And even though the H is the same, the pressure will be much higher. Yeah? But this doesn't have to be water. It could be anything, like gas as well. So we can actually use this formula when we're in the gas, like right now. Or, no, just can't. Stop, go away. So the H, if we go further down, the pressure goes up. So likewise, as we go up, the pressure goes down. And this is why, when you go on the top of high mountains, you need to take oxygen with you. Yes, because the pressure is dropping as you go up. And you can see that exactly from that formula there. Okay? You need to write that down. I'll go back to here. So the most important result here is that pressure is proportional to the density, bigger density, more pressure, and it's also proportional to the depth or the height. Did you write it down? Yeah. Okay, we'll just wait a minute then.
Are we going to do principle of flotation?
No, not really, no. This is Archimedes principle.
Yeah.
No, it's not on the course. It's not that difficult, I know. Okay, do you have this? Can I just go down?
Yeah.
Okay, so if we go down.
Do we have to include R goes to 0?
No, I'm just really making the point that you don't care about the shape of the object actually. So it could be a point, it could be a person, it could be a car, it could be a coin, doesn't matter. The pressure depends only on the height and the density, not on the shape of the object. Yeah, okay. Right, so a little bit more about pressure. Okay, so I'll just draw a little, I don't know. This is going to be a pipe. Kind of related to what I just did a moment ago. If you pick any point here and compare it with the same point on the other side, the pressure must be the same, because the only thing that matters is the height. And this is actually useful to know. So the only thing is the height. So the pressures at the same height, no matter what the system, should be the same. Okay? So for example here with our pump, if we pump the water up a hill, what do we think about the pressure here compared with the pressure here? Should it be the same, more or less?
More.
So P1, bigger or smaller than P2?
Bigger.
Smaller. Because this is higher up. So it has less pressure.
Oh, yeah, because
Because it's higher.
but if the height is bigger, so
Yeah, but unfortunately the H here is not really height but depth.
The depth here is the one to be like.
Yeah, the depth is decreasing. It's less down. Yeah, think about it like this, okay? Our H,
where are we taking the height from?
the height is taken
From the ground?
from the ground. From the ground.
So it's bigger, so P is bigger. The bigger H is in the formula, the bigger P is.
Yeah, but wait. If you're taken from the ground and the H measures below, then when it's other way around, it's a negative. So then it has the opposite relationship.
So
Wait. Which is bigger? -4 or -5?
more.
-4. The one with the smaller number. So because this is the other way upside down.
Let's say the P2 is 4 meters above and P1 is 5 meters above.
Yes.
Yeah, so 5 is bigger than 4.
Yes.
So
But they're negative numbers.
why?
Because we measure down as positive.
Can we
Because remember in my proof.
Oh, okay. Remember that was positive.
Yeah.
if you take them as negative, can we take 0 if it's 2?
Yes, but yes. We should just keep it to the way it's set up in the diagram.
Just keep it.
Yes, transition.
Does that mean houses in fourth floor of an apartment has a lower?
Yes, absolutely, yes. So if this is an apartment building, the water at the top, coming out the tap, be a lower pressure than at the bottom. Okay. Is this something?
That explains it.
You've noticed, have you noticed this?
Pressure at the bottom of the tank.
Yeah, so if you ever have a choice between being at the top or the bottom, you're better off being at the bottom because your shower will be a higher pressure.
Yeah.
Yeah, you're all going like, yeah, I've noticed this before. Do you all live on the top floor of an apartment or something?
No, I live on the second floor, my friend lives on 15.
Really?
Yeah.
And you can notice the difference with the
Yeah.
water? Okay. Yeah, that's good to know. That's good to know. So you're right, Hamish, pressure drops. Okay, so we're talking about here, this is pressure. If I go back to this example here, if these weren't equal, the water level will change to make the pressure equal. In other words, pressure always tries to equalize. Yes. What?
So why do they put tank up so?
Yeah, so you want if you have the tank up really high, then you don't have any problem with the pressure now, because if the tank is at the top of the building, then what will happen is the people at the water is falling down, so the water will get to everybody. Okay? But if the tank is at the bottom, then the water has to be pumped up, so you have to put pressure on the water, and then you have a possibility of the water not reaching the top floor then. Yeah. So by having a tank at the top, you guarantee that the water will reach every level underneath them. Okay, pressure will always try to equalize. So the example here, if you have something here with a pipe or a container, and the pressure here is high, and then the pressure outside is low, if there is a hole in the tank, what will happen is this gas or liquid or whatever, it will leave, and it will continue to do this until the two pressures are the same. Okay, so if we think about a water pipe, this has a high pressure so that it can reach the top floor. But if there's a leak in it, what will happen is the water will fly out, and it will continue to do this until the pressure here in the pipe reaches the same pressure outside, which is, what do we say, 1.01 times 10 to the 5. Yeah.
So the pressure in the pipe is more than that?
Must be more than this. In fact, I believe it's normally 3 times the pressure of the atmosphere. Which actually just reminds me, I should say 1 atmosphere, we call that 1.01 times 10 to the 5 pascals. So this here is about 3 atmospheres of pressure. And interestingly, if the pressure somehow was less than 1 atmosphere, what would happen? In the pipe, if it was less than 1 atmosphere, the air gets sucked in. And this is what happens for your vacuum cleaner. Your vacuum cleaner?
Is it low pressure?
Yeah, there's a pump. There's a fan which will drop the pressure inside the vacuum cleaner, so the air gets sucked in to try and equalize the pressure.
So the lower pressure inside the vacuum cleaner, the better vacuum cleaner.
Yeah, and the more powerful the fan, the more able it is to drop the pressure. So yes, the better it is then. Okay. So we have many examples of using pressure to help us do tasks, to do jobs. Okay. I don't think there's anything else to say about pressure. It's a very simple concept, and there's only one formula. Pressure equals force over area. Just be familiar with the language, okay? So we have 1 atmosphere is how much? 1.01 multiplied 10 to the 5 pascals. Do you all know those helium tanks for filling up balloons? Yeah. Just remember, you cannot use all the helium inside of it, because I said if the pressure in the tank is more than 1 atmosphere, what will happen? It will leave. Yep. Until the pressure in the tank is 1 atmosphere. So you can never get all the helium out of the tank, because it will just decrease to 1 atmosphere. The only way you can get the remaining helium out of the tank is if you put your tank inside a vacuum. Then you'll suck the rest of the helium out. Okay. the business teacher,
It's not between all gas.
yeah, it is, yeah. The business teacher, his wife makes those, you know, big balloon designs, you know, you make them into different shapes and
The
stuff.
one that you fly on.
No, this is for party balloons, you know, so like maybe around the door you have a balloon arch or something. So they buy these big helium tanks, you know, and in fact one of the exam questions was about helium tanks, and this is something that students forget. When you have like a tank, its pressure will decrease to 1 atmosphere, not to 0. So this will be a mistake in the exam, to say that it drops to 0. It drops to 1, it can't drop to 0, okay? So these questions are there, you can do them in a couple of minutes. You don't need to do number 6. It's not related to what you need for the exam. So you can do 1 to 5. And you can try 7. Yeah, okay. 1 to 5 and try 7. And then in a few minutes we can have a look at the lab report and I'll give you feedback. We're missing 2 Mohammeds. Is the other ones Mohammed Abdul Wahab? He's still sick?
Yeah.
He's very sick?
Yeah.
When is the Griffith College radio talk or whatever it is he's doing?
I think tomorrow.
It is tomorrow like 11 or something, isn't it?
Yeah.
Will he find himself feeling better by then?
Hopefully. He's doing working with I.
He is really sick?
Yeah.
And what about the other Mohammed? Oh yeah, sorry. Joshua, you were looking for lab 4, wasn't it? Yeah, you were looking for lab
2.
2.
Actually, all.
Where did I
2
do it?
people.
Here, I'll give you 2 and 3 for the moment. You'll have to take that for the moment. Gee, you're not even thinking of 4 yet. You're just 2 and 3 inside.
I haven't scared.
Well, you lost your one too.
No, I haven't.
What you mean to say is you forgot to take one when you were doing the lab. Yes, okay. Which one do you need?
Oh, 2nd of March.
4.
2nd of March.
Huh?
That should be.
I think that's wrong.
You can't argue with the paper.
So I told you it's due, this is the second one, on Monday.
This is 4.
Oh, it's 4, alright, that's fine. No, that's wrong, that date is.
No, it's not.
I'm sorry,
They
I
said the
did.
2nd of March.
This is the 2007.
Sorry, well, I'm happy with the date. Will you stop reading it as if that's in charge and not me, okay? I'm telling you the date.
No, please, 23rd.
The paper says.
Guys, the copy, I know it's difficult, try not to be stupid, okay? This Monday, lab 2. Following Monday, lab 3. And the following Monday,
Give us 2 weeks.
oh yeah, there's a holiday week. And then,
That's why.
2 weeks holiday.
Yeah. 3 or 4.
1 week holiday.
Yeah.
Before the week before we don't need the first.
Yeah, exactly. We don't have class, so we have that week to finish.
You don't have class.
We have the holiday, then the next week we start work.
Stop. Now we need to make sure, hang on, we need to make sure we got the dates clear. Today,
Today is our last day session in this week.
lab 2 is due the 2nd of February. Next week. Are you in on the 9th of February?
No,
Or do you have a holiday?
we just,
When's your midterm break?
16.
Alright, so then lab 3 is due on the 9th.
Yes.
No,
No.
not
No, it's Steven.
Why not? What's wrong with the 9th?
We have to submit other times.
For all the assignments, you say that the lab 3 is due on the first day of after the holiday.
Is it really?
Yeah.
Alright, well look. I will go with what Lorraine emailed you because this is the date that will be given to Sylvia so she knows when to expect them, okay? So can you just send that email to me? I'll double check the dates.
Is that for lab 3 or
For the
after meeting?
No, well, she's getting it now.
Probably not.
23rd is which lab?
Good.
And then lab 4 is the 2nd of March?
Yes.
Alright, so much
The
time.
paper was right.
But it's weird because I made the paper and the calendar, and this is coming as a surprise to me. Alright, just send me that email to confirm it. But anyway, right now it's lab 2 due on Monday.
Yeah.
That we all agree on, yeah?
Yeah.
And we can deal with that, and then next Monday I'll double check. But yes, I suppose it would be better to give you a little bit more time. Since,
I suppose you
thank you, I'll check it.
It's only more work than medicine students.
Do you think so?
There are just 2 lab requests and 1 chemist protocol.
Yeah.
4 lab requests and 1 chemist.
They just have 2 bio to write.
And we do have, and they have this draft and the final draft system.
Do you want this draft system?
But
No.
we're better than medicine.
Yes, yes, no, it's true, I agree with you.
The only problem is that